Welcome all to this new session of Chapter 16, the planar kinematics of rigid body. In this session, we are going to discuss the relative motion analysis of the velocity. So as I said in the beginning, we have one single objective here. So this is not objectives, only one objective, which is studying the velocity using relative motion analysis. So as we discussed previously, there are three types of rigid body motion: translation, rotation about fixed axis, and general plane motion. What we are doing here is trying to analyze the general plane motion using the relative analysis. So starting by the position, we said we have a fixed coordinate system and a translating coordinate system. The translating coordinate system is attached to one point, point A on the rigid body. And when the rigid body translates, we have absolute positions of point A and point B. And there is a relative position vector RB with respect to A. So if we want to express the position of B, then RB is equal to RA plus RB with respect to A. Now, to express the displacement of a general plane motion for a rigid body, it's the change drb in the position vector. So this is drb equals to dra plus drb with respect to A. Now, if you remember, when we took the time derivative of the relative position vector, if we have only translation, that went to 0. But here we have two motions. First, this body, which is a rigid body, we have 2 points in the rigid body. If you see, in general plane motion, it is not necessary that these two vectors will be parallel. So, because the body went into translation and rotation. So, and this is exactly what we are going to do. We are going to split the motion into two motions. First, we will assume that the body has just translated from this position to this one. And for that, this change in the position vector over here from A to A in the translating coordinate system and B from here to there they are just parallel. But the next motion is going to be assumed as rotation about point A. So, and this is why the body just moved to here. And for that reason, the location of point B, which is called here P prime, is actually going to move to here. So, to conclude, we will have the displacement here of B, which was due to translation and then rotation. This movement was made by the rotation, and this can be calculated by considering this position vector, the change in this vector, plus this vector, which is right here. Now, if we do the same analysis and we say that if we have a general plane motion, but now we want to study the velocity, then we do the same. We say that the first part is considered to be rigid body translation, and the second part is rotation about point A. So we know that when the rigid body translates, every single point on the rigid body will have the same velocity. So whether it is point A or point B, all of them will have the same velocity, and we call it VA. But we have to add the rotation about point A. Now, the rotation about point A is very simple. We know that if we have a rigid body motion and which is rotation, then all what we need to do is that we need to multiply omega by r. So this is the velocity of B is going to be Vp with respect to A is equal to omega multiplied by Rb with respect to A. So this is just a representation of the vector. So this is the velocity of A, and this is the velocity of B, and this is the relative velocity vector. So from the previous slide, if we want to represent this mathematically, we would have drB over dt, which is equal to dra over dt plus drb with respect to a over dt. Now, clearly this is going to be the velocity vp, which is equal to va plus vp with respect to a. And the reason why the derivative of the relative position vector came out to be a relative velocity vector is due to the reason that the rigid body here is assumed to be rotating about point A. So this is why if this is point B, and we will have omega, and this is the position R. So this is the velocity of B is going to be omega R. That's the reason. So to summarize, the velocity of B, this is the absolute velocity of point B, and here we have the absolute velocity of point A, and then we have the velocity of B with respect to A, which is due to rotation omega R. Now if you want to write that mathematically, we will have VB with respect to A, which is equal to omega cross RB with respect to A. So we will have the final velocity of B equals to the velocity of A plus omega cross RB with respect to A. Now what you should know here is that omega has no AB. It's basically, since we have one rigid body, then omega is the angular velocity of the body itself. If we have more than one body connected to each other, we might have an angular velocity of one body different than the angular velocity of another one. And what you should know is that B with respect to A is the relative position vector drawn from A to B. So if you say B with respect to A, you are actually drawing the vector from A to B. Now, the procedure for the analysis, especially when you deal with this in a vector equations, is to first establish the direction of x and y. Then you try as much as possible to indicate the direction of the velocity VA, VB, omega, as well as B with respect to A. Then you use this equation, which is the relative velocity equation, and then you evaluate the cross product. And after that, you have to equate the I component and the J component. As you probably remember from math courses, that this equation has two components, and you can equate the I component on the left-hand side with the I component on the right-hand side, and then the J component from the left-hand side with the J component from the right-hand side. And then you can solve for omega and VB. Also, don't forget that this is the positive direction of the cross multiplication. So if you cross I by J, you get positive K. If you cross J by K, you get positive I. And if you cross K by I, you get positive J. Here we will have several exercises on how to determine the direction of velocities, like at point A, B, or C. So in this example, point A right here is translating along this line. So as you see, if the A can have a velocity direction like this, or in the opposite sense. While if you look at point B, B is point on the circle. So if you have any point in the circle, all what you had to do is to draw the radius from the center to that point, and then you draw a line perpendicular to it representing the velocity at that point. So this is definitely going to be like this. And as I said, This is perpendicular to the radius. This is another example. In this example, if you look carefully here, we have the crank, which is this part, AB, is rotating. So if you try to draw a trajectory of point B, it's going to be just a circle. So all what you have to do here, if you want to draw the velocity, is to have it perpendicular to the crank, so which is tangent to the path. So this is the velocity at point B, while the velocity of C is in this direction. It can be on the other direction, which is this one, but it will always move in this horizontal motion. This is another example where point C is always moving along this slide. So we will have the velocity going in this direction, for example, while point B, without any confusion, has to be perpendicular to this arm. So just focus on this fact that this has to be perpendicular to this arm. This is another example. So we have the velocity of point C has to go always in this direction. So here it's not difficult, it's moving downward, so the velocity vector will go like this, while velocity of B has to be perpendicular to the crank, and it will go like this. And again, just to remind you that this has to be perpendicular to the crank right there. Now this is another example, and let's start with point C. Now point C is going to move along this horizontal, so it's not difficult to determine where the velocity is. It's just going in this direction. While it's a little bit confusing, maybe, with point B. But to make it easy on you, just don't forget that point B, if you look at it with respect to this arm, which is connected right there, pinned at point A, point B has to be perpendicular to this. Now, if you consider this one as your reference, this arm as your reference, you will not know if this is perpendicular or not, because this one is not only rotating, it's rotating and translating. So if you focus only on AB, then the velocity of B would have to be perpendicular to AB. And this is how we can determine the velocity of B. Now let's have a full example. So in this example shown in this figure, we have the bar AB right here of the linkage shown has a clockwise angular velocity of 30 radians per second. So that's a clockwise, omega equals to 30 radian per second. When theta, at the instant when theta equals to 60. So this is just at one instant when theta equals to 60. We want to determine the angular velocities of BC and the wheel at this instant. So we want to know what is the angular velocity of this one as well as the wheel. Now we will start the solution by considering the link AB, because link AB has one single motion, which is rotation about fixed axis at point A. So we start with link AB, and we can find the velocity of B as omega AB cross RB. So to show you those vectors, we have VB, which has to be perpendicular to AB. So that's VB. And we have omega AB, and the position vector is from A all the way to B. That's RB. So if we write this in a vector notation, then we will have minus 30k as a vector crossed by 0.2 cosine 60 I plus 0.2 sine 60 j. Now let us discuss this. First of all, we have the x and y axis in this direction. So if you cross I by j, you will get a rotation which is k in this direction. But what we have is omega going in the negative direction, and this is why we have to put minus sign. So this is minus 30k. And then we cross this by the position of point B. The position of point B is composed of two components. So the first component is an x component that's RBX, and then the other one is a j component, so RBY. And clearly, this is pointing toward the positive x, and this is pointing toward the positive y, and this is why we have them both positive. So this is, the angle here is 60, the length of this one is 0.2, so 0.2 cosine 60i plus 0.2 sine 60j. And what we are going to get is this, 5.2 I minus 3.0 j meter per second. Now let's move to length BC. Now for length BC, which is right here, we have a general plane motion. So if we want to write down the velocity equation, then VC is equal to VB plus omega BC cross RC with respect to B. Now, if you look here, that's the velocity of point C with respect to the point B. So VC is equals to VB plus omega BC. So omega BC is the angular velocity of this arm only, because this one has different angular velocity, this one has different angular velocity, and this one has different angular velocity. So let's now write down the equation. Now, what we know from this equation is that VC at this instant, VC was, while it is in the horizontal line, it will have a velocity acting on the horizontal direction. And for that, we can use this to our advantage. This is a very important information. So we can say that VC as a magnitude is just unknown, but knowing the direction is very important information. So we know that the direction is I. And then we have the velocity of B, which we just calculated from the previous slide. So this is 5.2 I minus 3.0 J plus, what is omega? Omega is unknown. So again, we can write omega as a scalar, omega BC, multiplied by its direction, which is k, multiplied by 0.2 I. Again, here the length of this vector is 0.2, and at this horizontal direction, it's pointing from B to C, and so it is positive I. So if we have this equation simplified, we will say that VCI is equal to 5.2 I plus 0.2 omega BC minus 3.0 J. So what we did, we just grouped the I component with the I component and the J component with the J component. So if we solve for the I component, we will get VC equal to 5.2 meter per second. If we solve for the J component, we will have 0, because on the left hand side we have no J component, is equal to 0.2 omega BC minus 3. So we solve for omega BC and we get 15 radian per second. And in this sense, it is acting in this direction. Why? Because we considered that omega here, when we say that omega BC multiplied by K, we assume that this K is the positive K. Positive K is coming from X crossed by J. So, which is I by J, which gives you, so let me just clear it up. So this is I by J, which gives you positive K. And since the answer came out to be positive, it means that our assumption is correct. Now the final part is the wheel. So for the wheel, we have only simple rotation about fixed axis. So we can utilize this equation, VC, which has just been computed, equals to omega D cross RC. So basically, since we know this velocity from analyzing this part, this velocity belongs to both BC as well as the wheel. So we can use this information to find omega D. So this is omega D multiplied just by its radius, which is RC. So if we write down the equation here, we will have the velocity of C, which we just computed, 5.2 I, which is equal to, again we assume that this is a counterclockwise rotation, which is going to give us positive K unit vector, and then we cross it with the position vector, which is here minus 0.1 J. Now why minus? Because if you look, the equation here says that the position vector is RC. Now RC is going from point D all the way to C, which is negative J. And for that, what we are going to get, we are going to get 5.2, which is equal to 0.1 omega D, and we will get omega D equals to 52.0 radian per second. So to summarize, we just found the position and velocity using relative motion analysis for general plane motion. We said that the position vector RP is equal to RA plus RB with respect to A. If we take the derivative of this, we will get VB, which is equal to VA plus VB with respect to A. Now, here, the relative position is no longer 0 as we take its derivative with time. And the reason is that because there is rotation and translation. And what we got is that this one is equal to omega cross RB with respect to A. That's it. Thank you.